Good day. Today we are going to be talking about my book, Finite Element Model Updating Using Computational Intelligence Techniques, which was published by Springer in 2010. So this series of lectures are going to go over each chapter, and today we are going to be talking about chapter 1 on finite element updating. Now, before we get into the details of what my talk is going to be about, the first thing that we'll need to understand, and it comes from the topic of the book, finite element modeling. What is a finite element model? A finite element model is used to approximate system through differential equations. For example, suppose you have a simple system. You have a mass, you have a string, it is hinged to the wall. So this mass can move to the other side if you apply a force. Now I'm going to write a differential equation that actually describes this system. The differential equation will be as follows: a mass multiplied by the acceleration of the mass plus the stiffness multiplied by the distance traveled is equals to the force as a function of time. So this will be a differential equation describing this system. It's a second order differential equation, and it is actually from Newton's first law of motion. F is equals to ma. The same system can be made a little bit more complicated if you add a damper. C is damping, so then the equation becomes m multiplied by the acceleration plus c multiplied by the velocity plus kx is equals to ft. Again, the mass multiplied by the acceleration, the damping multiplied by the velocity, the stiffness multiplied by the distance is equals to the force. Again, F is equals to ma. Now, how does finite element modeling actually works? Finite element modeling works by dividing your structure into small pieces and joining them together and analyzing how each piece behaves. And then when you join it, you can be able to model a complicated structure like an aircraft, a car, and so on and so forth. Where has this finite element model been applied? It has been applied in areas such as aerospace engineering, mechanical engineering, civil engineering, electrical engineering, and so on and so forth. So it is a very important aspect of design. But when you design something, you first have to model it in a computer, and if it is a complicated system, that modeling is going to involve finite element modeling. Now, where else have finite element models been used, and how have they been used? They can be used in vibration to analyze vibration of a structure. For example, if you design a car, you want to know whether when you are driving it, it's going to be bumpy. How is it going to respond when it comes to the roads? And that we call vibration analysis. And you can use finite element models for vibration analysis. The second example where finite elements have been used is in fatigue analysis. Fatigue, in English, it basically means to be very, very, very tired. Now, any system that is working, whether it is a car, it will have components that are going to fail because they have been used many, many, many times. So that is why you call fatigue analysis. Instead of taking a piece of an instrument and using it over and over and over and over and over again until it fails, and then you know when it is going to fail due to fatigue, you can basically be able to use a computer model that has been designed using finite element analysis to be able to know when fatigue failure is actually going to happen. So it's very important, without having to construct that object and run it up to failure. Heat transfer analysis is another example where you can use finite element modeling. For example, if you are going to design an air conditioner for this room, you can be able to use finite element modeling to be able to understand how energy is going to be distributed in the room. So it's actually quite important. How does it work? Here I have an example of a cylinder. It's just a cylinder. And then in order to analyze it, we divide it into what we call elements. For example, these will be elements. These are elements. And each element has nodes. So basically, when you do finite element modeling, you are going to basically specify the characteristics of each of these elements. Their material properties, how they are actually structured. We call it, is it a beam? Are you going to use a beam to represent it? Are you going to use a shell? And so on and so forth. And then, by analyzing how they behave and how they interact with their neighbors, you can be able to have a global view on how this cylinder is actually going to behave. And for me to do this, I used a software package called Abacus. It's quite an art to be able to do this, because the size of the beam of the elements can be optimized. You know, so there is a whole science around how do you make a good finite element model, which is beyond the scope of this talk. Now, the mathematical that I have written them, what I have written here is what we call a single degree of freedom system. Why do I call it a single degree of freedom system? Because it only moves in one plane, in the x direction. It could move in the x direction, the y direction, the z direction, and rotate around the x direction, the y direction, and the z direction. And then that will be a 6 degree of freedom system. Now, if you have multiple degrees of freedom, then the equations have to be written in the form of a matrix. A matrix. For example, if I were to write a simple system that looks like this. So you have the stiffness 1, then you have your mass 1, then you have another stiffness 2, then you have mass 2, then you have movement of mass 2 and movement of mass 1. This equation can be written as follows: m1 0 0 m2. This will be a mass. We call it a mass matrix. Then you multiply it by x1, x2, double dots, This is a vector of acceleration of mass 1 and mass 2 plus K1 plus K2 minus K2 minus K2 and K2 multiplied by x1, x2. All these are equals to the force that has been applied in mass 1. Let's suppose only F1 was the one where you applied the force, and then here it will be 0 because you have not done it. Now what have we done? We have represented this system as a matrix. This is a vector, this is a matrix, this is a vector, this is a vector. So basically what you have done, you have said M matrix multiplied by X vector double dot plus K matrix multiplied by X vector is equals to F vector. And that's basically what you can be able to do. And the power of this is you can have these matrices to be in the order of millions. For example, if you are analyzing the finite element of an aircraft, it's not going to be a 2-degree of freedom system. It's going to be thousands and thousands and thousands. This is a 2-degree of freedom system. So what would happen is that this mass matrix might be 1,000,000 by 1,000,000. And therefore you can't be able to solve it with your own hand. You have to use a computer. Now, while you are taking a structure, dividing it into small pieces so that you can be able to analyze it, there are certain things that you need to choose. One, the elements. We talked about the elements. So you have, let's suppose you have a simple structure, just a beam. You divide it into elements, and the elements probably will look like this. So you have 6 elements. Now, one of the first choices you will have to make is, what elements are you going to use? Is it going to be beam elements? Is it going to be plate elements? Is it going to be shell elements or solid elements? Of course, here it will be a beam because it is a beam. But if it is an aircraft, you will have multiple elements in one system. And then while you have done that, you have to also worry about something called the basis system, which is really the basis function is a function that is used to construct your differential equation. The other problem that you will have to deal with is, how do you model the joints? Complicated structures or shapes, how do you model it? Do you use linear or non-linear finite element model? The one that I have just written is actually a linear second order differential equation. But if the system is complex, for example, it's made out of plastic instead of made out of aluminum, then it's probably non-linear and your equations becomes more complicated. How do you model damping? One of the biggest problems that we have actually been dealing with in this area is, how do you model damping? Normally, if it is aluminium, then the damping is going to be assumed to be proportional, so because it is lightly damped, and you can more or less use proportional modeling, but that is another area that you have to deal with. How do you know what are the material properties of these elements? If it is aluminium, what grade of aluminium? If it is steel, what grade of steel? That information that you can just go and pick up from a chart might not necessarily be correct. Because of all these choices that you have to make, you obviously are going to get different answers. Sometimes answers will not even reflect the reality, and that is why finite element updating, and I'm going to talk about that later. Now, after after you have constructed your finite element model, what do you want it to predict? Do you want it to predict forces as a function of time? If you want it to predict forces as a function of time, we will call it a time domain finite element. If you want, or you might want it to predict the frequency spectra of your system. The frequency spectra, the time domain will be like this. Maybe x as a function of time. Call it a time domain because it is represented in time. The frequency domain probably will be a spectrum. Now I'm just going to write the magnitude of your frequency of your frequency. Probably will look something like this. You can have the modal domain. The modal domain basically is the representation of your system in terms of what we call modal properties. What are modal properties? Modal properties are natural frequencies and mode shapes. What are natural frequencies? Natural frequencies are the frequencies at which a system can actually vibrate. And they're very important for other reasons. When you design a bridge, for example, you have to know what your natural frequencies are, because otherwise, if they're excited, the bridge is going to collapse. We have had a bridge that collapsed because of that in the 40s in California, before they understood the significance of natural frequencies. The mode shapes, what are the mode shapes? For example, each natural frequency has a mode. For example, if we were to vibrate this beam, the first mode will just be the flapping. So it's like this. So it's flapping. The second frequency will be and so on and so on. And so each one of them has a natural frequency and a mode shape. Now we can go back to that equation that I talked about. mx double dot plus cx dot plus kx is equals to f. If you were to take it to the modal domain, then it becomes m minus m omega squared multiplied by m, and then you multiply it by the mode shape, plus I'm gonna assume that damping is 0. Let's suppose c is equals to 0. Then k mode is equals to 0. The reason why I'm assuming c equals to 0 is because if you don't assume it, your whole problem becomes complex. Now what does it mean here? It means the same thing that you represent as follows in the time domain can be represented as follows in the modal domain. Does that make sense? And then you can even go to time frequency analysis and so on and so forth, which are beyond the scope of this talk. Now, where lies the problem? For those cylinders, the cylinder that I showed, we went and modeled it using finite element model. These are the natural frequencies that we got for that system. We go and model it using finite element modeling, and then we predict what the natural frequencies are going to be. And at the same time, we go and measure the real cylinders in a lab. And after you measure, you get the measured natural frequencies. Now, what is the problem? I mean, this is lab, this is what the model does. So you can see that 2422, 2520, little bit of a distance. 433, 413. Quite a bit of a distance, and so on and so forth. So why is it that your finite element model does not predict your measured results adequately? The reason is because modeling is a complicated business. The material properties, the shapes that you are modeling in the model, the joints, all those things, if you don't model them correctly, that is what you are going to get. It might be that maybe your finite element model was a linear model. You needed it to be a nonlinear model. And that is the reason why. Now that is why we have this field of finite element updating. What is finite element updating? Finite element updating is a procedure of making your model predict your measurements better, so that your model is more accurate. And how do you do that? How do you bring the model closer to measurement? And what measurement? Is it measurement in the time domain as I have specified? Is it measurement in the frequency domain? Is it measurement in the modal domain? Or is it measurement in all these domains? These are some of the research questions that needs to be answered. How do we know that we have such a thing such as the correct model? Is there something such as the correct model? Or we just have a model that is sufficient to be able to do what we want to do with the model? Of course, as I have already indicated, finite element updating is basically has an objective of bringing the model closer to reality. And how is this done? How do we bring a model closer to reality? For example, we do know that if we have a system K and mass, that this system can be written as M, this is X, this is F, mx double dot plus k x is equals to ft. Now if you were to go and measure your x, your velocity and your acceleration and your forces, and your finite element model is nothing but just the m and the k, you can be able to identify the m and the k by doing an optimization process, which will make sure that if you put the m and k that you predict it will, and multiply it by the acceleration and the velocity that you have measured, it will give you the force that you have put forward. So in other words, you can be able to identify the correct mass and stiffness from your distance, acceleration, and your force. Does that make sense? Now if you were to go to the, and this is in the time domain, if we were to go to the modal domain, now you have your omega squared m phi plus k phi equals to 0. You can say that after I have measured my mode shapes and natural frequencies, the correct finite element model is that with the mass and stiffness, which if I multiply them by omega squared and mode shape, it will give me 0. So we have an optimization problem. That's what we do, you know. So you are exploiting the mathematical relations in order to be able to identify the correct parameters of a finite element model. Of course, this is a single degree of freedom, so it is easy. But if it is a finite element model, this might be 1,000 by 1,000 matrix. This might be 1,000 by 1,000 matrix, and this will be a vector of of 1,000 by 1, and omega is a scalar. So that is really, and there are many methods that have been actually identified to be able to do finite element updating. Matrix update method, which is the one that I've just talked about, optimal matrix method, sensitivity method, iterative methods, Bayesian methods, and computational intelligence methods. Computational intelligence methods are methods that are outlined in this book, and they're going to be topics of this discussion in the next lecture. Now I'm going to end up with the contents of this book. Of course, the details will come chapter by chapter, but this is what this book is all about. We have a chapter on just optimization. Now, what are you optimizing? You are optimizing an objective where you want your finite element model to be as close to your measurement as possible. And the optimization method that we are going to use in chapter 2 is Nelder-Mead simplex method, which is a non-gradient method, sequential quadratic programming technique. And then later on, we'll solve the same problem using genetic algorithm, which is based on the principles of simulating natural evolution, where the survival of the fittest is applied to a population of individuals. So you will have all these possible finite element models, and using genetic algorithm, you are going to basically choose the fittest one. Which is the fittest one? The fittest one is the one that is able to predict your measurements better than others. Then we are going to move on to particle sum optimization. Again, we will be solving the same problem. This is based on, it was developed by Kennedy and Eberhard, and it is based on the concept of modeling the flocking of birds. And again, we are going to use this for finite element updating. Then simulated annealing is another method that we are going to use. Simulated annealing is also another method that is based on the principles in which the annealing process in metallurgy actually works. Then we will move to response surface method, because some of these finite element models are so big that you cannot be able to even run them in less than 5 days on a normal computer. So how do you do that? You can be able to construct your objective. You approximate your objective by a simple function. And in this book, we approximate it using the multi-layer perceptron neural networks, which is a computational intelligence technique in order to solve this. I talked about the domain in which you do your finite element updating. Is it in the time domain? Is it in the frequency domain? Is it in the time frequency domain? In fact, if you do your finite element updating in the time domain, it turns out that the prediction that you are going to make using that finite element model on data that is on the frequency domain will not be as good as the prediction that you make on the time domain. So the prediction depends on what domain did you use to update your model. Now you can use what we call multi-objective optimization, where one of the objectives is in the time domain, the other objective is in the frequency domain, the other objective is in the time frequency domain, and you combine those objectives and you have a multi-criteria updating method, so that you are able to manage the fact that if you update in one domain, you perform poorly when you predict in another domain. So I have a chapter on that. And then the last one is the updating problem a deterministic problem, or is it a probabilistic problem? And if it is a probabilistic problem, we are obviously going to use Bayesian statistics in order to be able to understand or to solve that problem of updating. Thank you very much. And then the next lecture is going to be chapter 2, where we will be proceeding with finite element updating using non-gradient methods. Thank you very much.